Yeah, Twitch says I'm live. All right, cool. There's even some viewers. Excellent. All right, let's get started. Um, so today we get to today. I'm very excited about today. Today is Vector Clocks Day. So last time, to recap, we talked about Lamport clocks, and the quiz question last time had to do with the relationship between Lamport clocks and causality. So in the context of this course, causality means the happens before relation, this thing. So the relationship between Lamport clocks and the happens before relation is this. If A happens before B, then that implies, this double arrow here is the implication arrow, that the Lamport clock of A is less than the Lamport clock of B. So that was what the quiz question was last time. It was, if you know that A happens before B, then what, if anything, do you know about the Lamport clocks of A and B? And this is what you know. So this is the relationship that you have between the happens before relation and Lamport clocks. But what about the other direction? If the Lamport clock of A is less than the Lamport clock of B, then is this true? Oh, really? Interesting. You're not seeing my, you're not, oh no, huh. Okay, just a second. Thanks for pointing that out. Are you now seeing the right thing in Zoom? Great. Sorry about the technical difficulties. All right. So, um, so now hopefully you see what I wrote down a second ago, which is we know the relationship of Lamport clocks and the happens before relation says that if A happens before B, then you know that the Lamport clock of A is less than the Lamport clock of B. But this implication in the other direction, do you know that? We do not. So we saw an example of that last time. So that's not true. So it would really be nice to have some sort of logical clock that did exactly characterize the happens before relation. Happily, such a thing exists, and it gets used all the time in distributed systems, and it's called a vector clock. So vector clocks were independently invented by two authors, Friedman Mattern and Colin Fidge. And they each independently wrote a paper about this in 1988. So here's the property that's true of vector clocks. If A happens before B, then the vector clock of A is less than the vector clock of B. And the implication goes in the other direction too. So if the vector clock of A is less than the vector clock of B, then you know A happens before B. So in other words, with vector clocks, we have both directions of this implication. So it's if and only if, not just if, like it was for Lamport clocks. So this is huge because it means that vector clocks like Lamport clocks, are consistent with causality, but unlike Lamport clocks, they characterize causality. So we say that vector clocks are consistent with and characterize causality. Okay, so what are these vector clock things? What is the definition of a vector clock? Well, remember, a Lamport clock is just an integer, right, that just gets assigned to an event. So what do you suppose, if that's what a Lamport clock is, what do you suppose a vector clock is? Magnitude and direction. Okay, maybe you're thinking of vectors in terms of physics. So if we think of vectors in terms of programming, a vector could have any number of dimensions, right? So before, we just had a single integer, right? So now we're going to have a vector of integers, or a list of integers, some kind of sequence of integers. So to dispense with any magic, a vector clock is just a sequence of integers. Here's how it works. So we say, first of all, every process maintains a vector of integers initialized to 0. Just like with Lamport clocks, every process kept a counter, right? A single number initialized to 0. For this, every process is going to keep a vector of integers initialized to 0. How long of a vector? How many do you think? Yeah, number of processes, that's right. So if there were 3 processes, then it might look like this. Okay, so before we wrote down rules for how these clocks get updated. So just like with Lamport clocks, we're going to use vector clocks to count events, but vector clocks are more informative than Lamport clocks. So if a Lamport clock is, let's say, 17, then that kind of just means 17 events have occurred that I know about. But if I have processes, Alice, Bob, and Carol, and I have a vector clock that says 1700, each entry in here is going to correspond to one of my 3 processes. So this vector clock of 1700 like this describes a world in which Alice has seen 17 events and Bob and Carol haven't seen any. So this is a more fine-grained understanding of what has occurred than Lamport clocks, right? A Lamport clock of 17 just says 17 events have occurred, but this says something about who's seen what events. Okay, so the next part of the definition. On every event, a process increments its own position in its vector clock. And this includes internal events as well as sends and receives. Somebody's asking a really great question in chat, which is, well, what if you don't know how many processes there are in the system? How would you do this? How would you handle this? Because, for example, here, I'm saying that every process is going to maintain this vector. So Alice, Bob, and Carol are each going to keep a 3-element vector because Alice, Bob, and Carol each know about Alice, Bob, and Carol. But what if the processes don't know about the other processes that exist? That's a great question. So vector clocks only work if you have this fixed ahead of time knowledge of how many processes there are in the system. So that's a terrific question. And that's in fact one reason why tracking causality with vector clocks can be problematic and why some systems choose not to do it, or they might choose to do it only with some subset of the nodes. But we'll see that this technique turns out to be pretty generally useful despite its drawbacks. Okay, so what's next? So we've seen every process is going to keep a vector, and on every event, a process is going to increment its own position in the vector clock. This is sounding not too different from Lamport clocks so far, except that you just increment your own position instead of the one number that you have. Okay, what about sending? So we say, when sending a message, each process includes its current clock. And this is after incrementing its own position, because a send is an event. So we'll say, okay, here's another question in chat. Two processes can have a new event at the same time. Right, so of course in the vector clock, you can only track the events that you currently know about, right? So this vector clock here of 17, 0, and 0 says that Alice knows about 17 events. Bob knows about 0 events, and Carol knows about 0 events. If another event happened, right, on Bob right now, say it was some event that was internal to Bob, or even if Bob just sent a message to Alice, Alice doesn't know about that yet, so Alice's clock can't increment at that point. We'll see more examples of that soon. Okay, and then the last thing that we haven't talked about yet is receiving, right? So what are the rules for receiving? When we talked about Lamport clocks, we said that your Lamport clock increments to the maximum of the clock that you receive on a message plus your local clock plus 1. So for this, we say when receiving a message, each process updates its vector clock to the max of the received vector clock and its own. And this is also after incrementing. Because a receive is an event also. So those are the rules on one page. But there's something that we haven't really defined here. So before, when we were just talking about Lamport clocks, it was pretty easy to know what maximum meant, right? We could pretty easily take the maximum of two numbers. But here I have this word maximum. So what does this mean in the context of vectors, right? If you have a vector of integers, two vectors of integers, and you want to take the maximum of those two vectors, how would you go about it? Does anyone have a suggestion? Yeah, take the max element-wise, sure. So this is sometimes called the point-wise maximum also. So the notion of max that we're going to be using here is point-wise or element-wise maximum. So if we have, say, two clocks and one of them is, say, 1, 12, 4, and the other one is, say, 7, 0, 2, what do we get when we take the point-wise maximum of those? Yeah, that's right. So we should get something like 7, 12, 4. Okay, good. All right. Now, how do we know when one vector clock is less than another? So before I wrote this, but I didn't give a definition for this less than comparator here. So we need to figure out how we define that. There's another question in chat. Somebody asked to see the definition of vector clocks again. Okay, so here are the rules for how to update vector clocks. I'll take a picture of it myself too. So it actually, as far as this whether you take the max first and then increment, I'm actually not sure if that makes a big difference. I wrote it that way in order to be consistent with sending, because of course with sending it matters, right? Because you want to make sure to increment your clock before you send it, because you need the correct thing to be sent there. But with this, it would be okay if you incremented your own clock value, I think, before taking the maximum. So that's not such a big deal. All right. So now that that's been saved and shared in chat, let's switch back to this page. Okay, so what we were wondering about was this less than thing here, right? Because this is true, right? I'm claiming that this is true, but in order for that to be meaningful, we have to know what less than means when we're comparing two vector clocks. So how do you know when one vector clock is less than another? So it's slightly subtle. We say that the vector clock of A is less than the vector clock of B when for all the positions in the vector clock, so we're going to call them, so let's say that these things, these vector clocks have elements, and they're indexed by I. So we could say at every index I, the vector clock of A at that index has to be less than or equal to the vector clock of B at that index for all I, and the vector clock of A is not equal to the vector clock of B. So this is a way to make this strictly smaller comparison between vector clocks. We say that the vector clock of A is less than the vector clock of B if for every index, the vector clock of I is less than or equal to the vector clock of B, but also they're not equal. So there has to be, in other words, there has to be at least one that's strictly smaller. So for example, we could look at an example of this. If we had, let's say, VC of A that's like 2, 2, 0, and VC of B that's 3, 2, 0, then that would be a case where we could say that the vector clock of A is less than the vector clock of B, because the vector clock of A is less than or equal to the vector clock of B, less than or equal to the vector clock of B in all the positions, and also they're not the same. So that's how we compare vector clocks. How about another one? How about this? What if we had VC of A being 2, 2, 0, and VC of B 1, 2, 3. So is the vector clock of A less than the vector clock of B here? This one is not. So it's not the case that the vector clock of A is less than the vector clock of B. What about the other direction? Is this true? Is the vector clock of B less than the vector clock of A? No, that's not true either. So in this case, the events that would get these two vector clocks attached to them are considered concurrent, because we can neither say that the vector clock of A is less than the vector clock of B, nor that the vector clock of B is less than the vector clock of A. So we would say that A and B are independent or concurrent. Questions about this so far? So there was a question about the definition here. So yeah, so we say that the vector clock of A is less than the vector clock of B if for every index, the number at that index is less than or equal to of A is less than or equal to the other one. So notice that this is a less than or equal to comparator here, not strictly less than. So it's less than or equal to. So it's okay if they're the same in almost all of the positions, right? In this example here, they are the same in all but one position, right? But there is one position where this one is bigger, and that's captured by this last condition here where we say that the vector clocks can't be equal. So let's go through an example, and let's talk about assigning vector clocks to events. So back to our friends Alice, Bob, and Carol. All right, let's see. I'm going to put a whole bunch of events up here. That should do it. Okay. So let's try to follow those rules that we had before and try assigning vector clocks to all these events. So we're going to start out with every process having its vector clock initialized to 0. And I probably won't update these up here as I go along. Instead, I'll just write the vector clocks of each event next to the event, and we'll try to keep track of what the local clocks would be updated to as we go along. Okay, so starting with Carol. So here's an event here. It's the first event that Carol knows about, and Carol doesn't for herself, and Carol doesn't know about any of Alice and Bob's events. So the vector clock here is going to be 0, 0, 1, because we're going to assume that that's the sequence of positions in this vector, 0, 0, 1. That's another thing that has to be the case with vector clocks. All of the processes have to agree on an order for the processes in the vector clock. So this is something else that would have to be known ahead of time in order for this approach to work. And you could have some ordering that made sense, right? You could use like lexicographical order of the IP addresses or something like that. But this would be something that the machines would have to agree on. Otherwise, your vector clocks would be nonsensical. All right. So this is the clock for this event right here, and just like with Lamport clocks, vector clocks get sent along with messages. So this clock of 001 is going to get attached to this message as it gets sent to Bob. Bob is going to receive it, and he's going to compare it with his local clock value, which is just 000. So, well, 001 is bigger than 000, according to the notion of bigger that we defined. So the bigger one will win. And then Bob, of course, also has to increment his own clock position. So this will become 0, 1, 1 right here, because Bob's position in the vector is this middle position. Okay, so then Bob has to send a message here. What should be the vector clock for this message send right here, this second event on Bob? Can somebody tell me? That's right, it should be 0, 2, 1. Message gets sent with the 0, 2, 1 on it. It arrives over here at Alice. Alice's local clock is still 0, 0, 0. But Alice is going to increment her own position in the clock when she receives it. So it's now going to be 1, 2, 1. Now here's a send from Alice. So the clock here should be 2, 2, 1 because Alice is going to increment her own position. Message gets sent over here to Bob. Oops, let's deal with this previous message from Bob first. So Bob sends a message here. What should the vector clock on this this message should be? It's the third event on Bob's process. That's right. This one should be 0, 3, 1. The message gets sent. Now Carol's current vector clock is 0, 0, 1, and that gets compared with this 0, 3, 1 over here. Those get compared. We take the pointwise maximum. This one wins. And then Carol's local clock gets updated. So this becomes 0, 3, 2 over here. Now let's deal with this one here. So here's a case where we have a clock that's coming in from Alice, right? We're looking at the fourth event on Bob now. We have a clock that's coming in from Alice that said 2, 2, 1. And then we have Bob's current clock that said 0, 3, 1. So how are those going to get combined? Yeah, we're going to take the maximum of them, of each position, right? So the maximum of 2 and 0, right, is going to be 2. The maximum of 3 and 2 is going to be 3. And we're also going to increment it, right, because it's Bob's position. So that's going to become 4. And then, of course, the maximum of 1, and 1 is just 1. So the vector clock of that event right there becomes 2, 4, 1. Let's just keep filling these out here. So this one down here is a send from Bob. Bob increments his own position there. So that one will be 2, 5, 1. Here's a send from Carol. Because it's Carol sending the message, she's going to increment her own position. So it's 0, 3, 3. That gets sent over here to Alice. What does Alice do? She takes the 0, 3, 3 and takes the pointwise maximum of it with her own clock, which was 2, 2, 1. And she increments her own position as well. So the max of 2 and 0 is 2 plus it's her own position. So the first thing becomes 3. The max of 2 and 3 is 3. The max of 1 and 3 is 3. So that clock is 3, 3, 3. This one over here, 2, 5, 1 gets sent from Bob to Carol. Carol's current clock is 0, 3, 3. How do those get combined? 0 and 2. The maximum of those is 2. 3 and 5, the maximum of those is 5. 3 and 1, the maximum of those is 3. And then it gets incremented because it's Carol's position. And then finally, this is Carol's last send. So this one will be 2, 5, 5. That one will get sent over here. Somebody want to tell me what the last vector clock will be for this receive from Alice? Yeah, that one should be 4, 5, 5. That's right. So there was a question about this 2, 4, 1 up here. So this one, so Bob's current clock right here is 0, 3, 1, right? And then Alice has 2, 2, 1. So the way that those get combined is you take the pointwise max of each element. So the max of 2 and 0 is 2, and the max of 2 and 3 is 3. But Bob is incrementing when you receive, that's an event on you. So you increment that. So there's a question: do you add and then increment, or is it okay to increment and then add? I think it actually works to increment and then add, but the way that I wrote it down in the definition before uh, was when you receive a message, you update your vector clock to the max of the received vector clock and your own, and that you do that after incrementing. But I think it would actually work to do it either way. Okay, so here's our full picture again. By the way, this is from Wikipedia, from the article about vector clocks, if you want to go compare it to what they showed. They have a slightly different way of drawing the picture, but it's the same information. Okay, so let's look at this event right here, this one that we dwelled on for a minute. Let's call it event A. It has vector clock 241. So now we can ask, what are the events that are in the causal history of this event A? Well, so based on what we know about the happens before relation, we know some things, right? We know that everything that came before it on its process line is going to be in its causal history. So let's look at those events and look at the vector clocks of those events. Well, what are those clocks? Well, there's this one had 0, 1, 1, and this one had 0, 2, 1. This one had 0, 3, 1. So if we look at those clocks, right, they're all less than this 2, 4, 1, right? Well, and what else is in its causal history? Well, there's these two events on Alice, right? They're in its causal history if we follow the, if we use our rule of thumb, right, that causality is graph reachability, right? Then we can see that these two events are in the causal history of A. And if we look at those clocks, they're also less than the clock on A. And then there's this event back here on Carol with clock 001. So that one is also in the causal history of A if you follow the path through the Lamport diagram here. So we have a bunch of events here, and I'll just circle the vector clocks of all the events that I can see that are in the causal history of A. So we can see that all those events are in A's causal history because we could reach A from them using that principle that causality is graph reachability in space-time that we talked about previously. But what you notice about all these vector clocks of all these events that are in A's causal history is that they're all smaller than A. And likewise, if we looked at an event that was causally later than A, we would see that its vector clock had to be bigger. So this event here, for example, is causally later than A, and its vector clock is bigger. And this one here is causally later than A, and its clock is bigger as well. Well, what about those events that have a vector clock that's neither smaller nor bigger than A? So for example, right here on Carol, there's an event, let's call it B. So this event has a vector clock of 0, 3, 2. How does that one compare with the vector clock of A? Is it bigger? Is it smaller? Right, it's neither bigger nor smaller. So we say that these two events here are independent. Or we say they're causally unrelated. Or we say that they're concurrent. Those things are all synonyms. So this is great, right? Because now, instead of having to think about graphs and reachability and all that, now, if we want to know if one event potentially caused another event, all that we have to do is just compare a bunch of numbers in a vector. Guess what computers are really, really good at? Computers are really good at comparing a bunch of numbers in vectors. So this is great, right? we've taken this really complicated notion of causality and we've boiled it down to just comparing numbers and vectors. And with that, we can exactly capture the happens before relation that we've been talking about. Computers are good at graphs too, but usually when they are good at graphs, it's because the graphs have been boiled down to some sort of representation that amounts to vectors of numbers, I think. So vector clocks are great, and they're really widely used, and we're going to see this concept of vector clocks coming back multiple times in this course. Questions about any of this? Yeah, somebody asked, okay, so why are A and B independent? Well, if you look at their clock values, so A has a clock value of 241, right? And B has a clock value of 032. If I looked at those two clock values, and you asked me which one is bigger, right? Well, if I tried to argue that this A was bigger, right, the 241 was bigger, then you could say, well, no, because this B is bigger in this last position here, right? And if you tried to argue that B was bigger, then I'd say no, because A is bigger in the first two positions. So neither of them is definitely bigger, right? So we know that it's not the case that one is less than the other. And so that's how we know that that these two events are independent. Whereas if you look at some event that causally precedes A, which would be any of these other circled ones up here. Maybe I shouldn't have circled this one because that makes it look as though it's part of this whole set. So think of this circle as being sort of a special circle here. But any of these other circled ones back here that are in the figure, these all have vector clocks that are less than the vector clock of event A, according to the definition that we're talking about. That's right. Yeah. So there's lots of other events that are going to be concurrent with A as well. Yeah. So this here, we'll give it the same special kind of circle, is also concurrent with A. Sure. So some folks are asking some questions in chat that I'm not sure I understand, but hopefully I can try to clear some of them up later. So one question is, if there's this 031, I think some folks were wondering about how exactly this 241 gets calculated here. So this, I think the key to remember is this 221 gets sent along here as part of the metadata on this message from Alice to Bob. And so this 221 gets sent along here. And so when Bob receives this message, Bob sees that vector clock that came along on the message and compares it with his own local clock. And so that's where we get the 2, right? Because 2 is the pointwise max of 0 and 2. The middle value, we take the pointwise max of 2 and 3, which is 3, but then we increment it because Bob is counting this event that happens on himself as an event. And so then we get 4. And then the max of 1 and 1 is just 1. So that's how we calculate the 241. Other questions? Here's the definition one more time of how you compute vector clocks. So here's a quiz question. and I'll share it. It's a little bit hard to read, isn't it? I don't know why. There we go. Here is the quiz link on Slack. Give people a little while to fill that out. Make it a little bigger so it's readable on Twitch. Should be a relatively easy one, I think. All right. So as the last few of the responses come in, we can start to talk about something new. So back in a previous lecture, I briefly mentioned this word protocol. So what did we say a protocol is? So we'll say a protocol is a set of rules that computers use to communicate with each other. It's not exactly a formal definition, but it'll do. Okay, so in particular, it's a set of rules that can tell you what messages you're allowed to send in terms of what messages you've received. Okay, so say let's think of a really simple protocol. So let's say you have a protocol where one machine can wake up and send the message, "Hi, how are you?" And the machine that receives that message can respond with, "Good, thanks." Or we'll say the machine must respond with "good, thanks" if it gets that message. So here's a Lamport diagram that describes a run of that protocol between Alice and Bob. So Alice says, "Hi, how are you?" Alice is maybe in a much more magnanimous mood than before when she said that Bob smells. Okay, so there's a protocol. All right, or it's a particular run of a protocol. How about a different run of this protocol? Well, Bob could be the one to ask, right? It could be this. So that could be another run of the same protocol. All right. So nothing in our description of the protocol said that Alice had to be the first to talk, right? So these are both valid runs of the protocol, right? Okay. So what about something like this? So that one is clearly a protocol violation, right? Not only is it violating the social protocol, but it's also violating this particular protocol that we just wrote down. Okay, so that's not allowed. Okay, what about this? So is the protocol being violated here? What do you think? Not yet. Yeah, that's a good answer. Yeah, this is kind of a weird case, right? Because these lines go on indefinitely. So it's not necessarily a protocol violation, right? Because the protocol could still be running, right? We might have just interrupted the protocol in the middle. In fact, maybe what this diagram actually looks like is more like this. Maybe it's like so maybe Alice is a little bit slow on the uptake, right? But if we cut off our diagram right here, right, we don't know. So in terms of Lamport diagrams, there's not any difference between this, what I have shown on this sheet here, and what I have up here, right? Maybe Alice is working from home, sure. So there's no difference in terms of Lamport diagrams between this picture where Alice responds fairly promptly and this one where Alice might be a little slow. Distance doesn't mean anything in these pictures. For that matter, there's no difference between either of those and one that looked like this, where Alice did respond promptly, but the message just took a really long time to arrive on Bob's end. So what that means is that when I talk about a particular run of a protocol and I draw one of these things, you should understand that they could mean different things in terms of physical clocks, but they mean the same thing in terms of logical clocks, that is, with regard to ordering of messages. But even though we know that the diagram where Alice quickly responds to the good thanks, and one where she takes longer to respond, even though we know that those are the same in terms of, perhaps in terms of Lamport diagrams, there's still infinitely many Lamport diagrams that describe correct runs of this protocol. For instance, you could have any number of back and forth exchanges, right? How are you? Good, thanks. How are you? Good, thanks. Ad nauseum, right? So if I asked you to draw a Lamport diagram that was some sort of complete characterization of this how are you, good thanks protocol, then you wouldn't be able to do it because there are infinitely many correct ways for a run of this protocol to go. So I usually won't ask you to do that. I usually won't ask you to draw a Lamport diagram that describes a protocol because it's not possible to do it, right? Because there are a whole lot of different, because a Lamport diagram describes a particular run, right? And there are multiple correct runs, often infinitely many correct runs of a protocol. So that's not something that you can do. What you can often do, though, is draw a Lamport diagram that characterizes a violation of a protocol. And we did do that a second ago. So we put a particular violation of this protocol was this one right here, where Alice just says, good, thanks, without being asked a question. So that's what we'll do quite often, right? So here's a question. Yeah, somebody asks, what if they both send hi, how are you at the same time, right? And maybe these messages cross over, right? So that would not be a violation of the protocol, would it? There's nothing in there that violates the protocol. So this is the only one that I've shown so far, this one where Alice just says, good, thanks, completely unprompted. That's the only violation that I've shown so far. So the reason I'm talking about this is because we're going to, in this course, we're often going to talk about violations of some sort of property, some sort of correctness property, as being embodied by a diagram. And so an anomaly is a run that violates the property that we want to have be true. And so a diagram can usually characterize that anomaly in some sort of meaningful way. So in particular, we're going to start to talk about some properties, some correctness properties that we want to have be true. And one way to kind of summarize those properties and kind of be able to talk about them is to draw a picture of a violation of a property. So let's see an example of that really quickly. So here's a particular correctness property. Actually, you know what? I'm going to call it FIFO delivery. FIFO delivery. If a process sends message M2 after message M1, any process delivering both delivers M1 first. So this will be confusing unless I explain what deliver means. We talked about sending and receiving, and those are pretty intuitive, right? So sending is something you do. Sending a message is something you do. Receiving a message is something that happens to you, right? You don't control when messages arrive at you. They just do or they don't. But delivering is actually something that you do with a message that you receive. So a protocol can wait to deliver a received message until the right time. So if you want to, you can receive messages and then queue them up until it's time to read them. This is actually a very important mechanism, which we'll talk about more later. But a violation of FIFO delivery would look like this. Or if you don't like the idea of arrows going backwards in time, then you could draw it more like this. So this is an example of a FIFO anomaly. FIFO delivery says that this particular anomaly won't happen. So we'll talk a lot more about this next time because we're almost out of time. And we're also going to look at some other examples of delivery guarantees that you might want to try to ensure. But this concept of delivery as opposed to receiving is very important. So just to recap, receiving, you don't control. Delivery, you do. All right, it's 10:25, so that's it for today. I will see you next time.